Hi everyone, I'm Katerina Fragkiadaki and I'm very happy to give this talk in this workshop on visual question answering with 3D visual feature representations. This is joint work with my students Fish, Mihir, Adam and Shamit. Let's start from a very basic question. What does it mean to comprehend natural language? We liked very much the answer we found in this excellent paper, Symbol Grounding and Meaning, the comparison of high-dimensional and embodied theories of meaning from Glenberg and Robertson. There, Glenberg and Robertson conducted some human studies where they had some human subject and they showed pairs of sentences which were grammatically and syntactically identical, but semantically different. Sentences like those, after wading barefoot in the lake, Eric used his shirt to dry his feet, versus after wading barefoot in the lake, Eric used his glasses to dry his feet. They showed that humans could very easily classify the two sentences as affordable versus unaffordable, possible versus impossible, while the word models of that time that reasoned about word co-occurrences but didn't know anything about the world, okay, and other like visual dimensions of glasses and shirt or size dimensions or affordances, how they're used, physics and so on, could not do this classification easily. Here's another example. He used the newspaper to protect his face from the wind versus he used the matchbook to protect his face from the wind. And this is these experiments are very relevant to this workshop because indeed it's remarkable how many questions humans can very easily answer if you describe them a situation in the absence of any visual input, just from memory, just from imagination. They can answer things like how many free hands the man has, and is the newspaper in front or behind his eyes, or is it single page? Is he holding the newspaper versus lying on it? Is the newspaper also covering his neck or his feet and so on? How humans can so easily answer questions about language descriptions of situations? What is the right supervision setup for machines to also be able to answer such questions, right? Do we just need to scale up our current data sets, or do we need to just allow more information, more world information about the world as opposed to static images come in? Glenberg and Robertson in their paper give an explanation regarding how humans process natural language. They say that words and phrases index into objects and prototypical symbols that retain perceptual properties like size and appearance and so on. And they derive affordances from those objects, what these objects can do, how can they be combined. And is this, let's say, is this process that essentially gives meaning to the utterance. All right, there's some indexing into some symbols, and these symbols have been acquired with constructs similar to perception and control, where people were looking and moving around. All right, so they understand utterances, natural language, through simulation of their content. And in this talk, we'll pursue also a similar approach. How can we go from language to simulation? And that simulation will be in some visual space. Now, the question is, in what visual space should the simulation be? Current models of language and vision can, they're scoring very well on the benchmarks and the numbers constantly go up, but they cannot actually infer affordability of language utterances. For them, the ball inside the cube versus the cube inside the ball, it's the same, right? They cannot really, protest and say, okay, the first one doesn't make sense. So the question is, how can we allow them to be able to reason about affordability? And our proposal here is very simple, is instead of going from associating language with images, like what we show on the left, what if we associate language with scenes? And we allow an agent, which we have an embodied agent because now he can look at a scene from different viewpoints. We allow an agent to go around the scene and see it from different viewpoints. And once you're allowed to see a scene from different viewpoints, then you can see things like that you cannot see from a single image. You can obtain 3D visual representations as opposed to 2D ones. And those 3D representations know things about objects having 3D extent, and objects do not interpenetrate in 3D. This constraint comes from free, and objects have regular sizes. For example, pens are smaller than elephants and so on. Objects persist over time, so there is object permanence, so things will not change as the camera viewpoint changes. These are very, very basic properties that will endow our 3D visual representations with. Okay, so in the next short part of the talk, I'll describe how we get those 3D representations from images, and then I'll show how to use them for mental simulation of natural language context for affordability inference and visual question answering with very, very, very small amount of labeled data. And most of the supervision coming from an agent moving around. So we'll use networks that we call geometry-aware recurrent networks. These are networks that map 2D or 2.5D, in case you have also a depth map image, to a 3D feature map. A 3D feature map is like a grid where in every XYZ location of that grid is a three-dimensional grid, where every XYZ location of that grid holds the whole feature vector. And here I'm not showing this feature vector. We've done PCA along the feature dimension, and we kept the first dominant 3D components, and we map those to RGB values. So that's why you see this color. So the way GRNs, geometry-aware recurrent networks, work is that they take a sequence of images and they estimate also the 3D rotation and translation of the camera from time step to time step, and they use that ego motion information to dump visual features into that 3D hidden latent canvas. So they separate camera motion from the scene appearance, and they build a stable 3D feature map of the world scene, and they're end-to-end trainable from the downstream task. And the first two bullets, for those in the audience that know SLAM, simultaneous localization and mapping, this is exactly what SLAM does as well. We have agents moving around and mapping 2D videos with 3D point cloud map of the scene and a 2D camera trajectory, right? And that point cloud map is indeed stable and does not change based on how the camera moves, but they are not end-to-end trainable. The big benefit of GRNNs is that after training, they will be able to map even a single image to the full, complete 3D feature map of the scene. Complete, I mean behind occlusion. So now I'm going to show you how we do that. It's simple. We're going to train GRNNs for view prediction. So this is how GRNNs work. Here we have a sequence of images of a static scene taken from a moving camera. As you see, there are multiple objects in the scene. Every image passes through an encoder. So this encoder essentially is a ray casting. It maps a single pixel along a whole ray. If you don't have a depth map, if you have a depth map, then it just places in the right 3D location on the grid using the camera intrinsics, and then uses 3D convolutions to densify that map. And in the next frame, you do exactly the same thing, but before accumulating information, before fusing those 3D feature grids, you first estimate 3D rotation and translation of the camera and use it to appropriately transform the 3D feature grid to bring it to the same coordinate system, to align it to a coordinate system of the first time step. So you do this again and again. It's as if the network learns SLAM in its latent bottleneck. The result of this process, of this coding process, is despite the fact that a particular pixel location changes all the time, location in the input to the stream, it is always mapped on the same 3D location, the hidden state. If you wouldn't do that, then the hidden state of the network would be dominated by the camera motion, right? Now we have a way to separate, to disentangle camera motion from, scene appearance in a very similar way as SLAM, but instead of using point clouds, we use feature grids that we can train end-to-end for a downstream task. And the downstream task we'll consider is view prediction. We have an agent that moves around, sees query viewpoints, and is asked to predict, is asking from its hidden state to predict that query viewpoint before seeing it, and it orients its map and neurally projects it, renders it to an image, and it goes to that query viewpoint and computes a loss. Okay, and we have later works that instead of using the objective, instead of being a Euclidean distance in pixel space, is a contrastive pixel ways matching, which is more robust to real world illumination changes and stochasticity of content and so on. Now, the benefit that you get from this architecture is that you can generalize across scenes. So here are scenes on the top. I show scenes of only 2 objects where we train the network. And these are scenes with 4 objects. So this is all input to the network. These are 3 time steps. You can also fit just the first time step, because after training, the network works from any number of images. And then you ask your network to predict what it sees from the scene from all viewpoints. And as you see, GRNs predict the different objects, and they render them correctly, and the objects are complete across occlusion, so on. While a network that has a 2D or 1D bottleneck as opposed to 3-dimensional bottleneck, as you see, it can still imagine 2 objects. It cannot really show this strong generalization. So what we achieve with GNNs is to map 1-to-1 every 3D physical point from the scene to a point in the 3D feature map. So now let's use now these 3D feature representations for question answering. Now we said that the first thing we'll do is exactly trying to answer these affordability questions. I'll give you an utterance, and the machines should say if this makes sense or not. So let's see how we can do this with those representations. We said that instead of associating 2D images with utterances, we'll instead associate scenes with utterances. And when I have a scene, I can view it from different viewpoints. So what I can do is I can train GRNs. I can train networks that map a single image to the corresponding 3D feature map. So then I will also consider, I'll train a semantic parser of natural language to give me the parse tree in terms of noun phrases and their spatial expressions. And then I'll use this parse tree to train compositional modular generative networks that map from noun phrases to 3D feature maps of the objects that they describe, and from spatial expressions to 3D offsets that they describe. Okay, so let's see what are these generative networks. Here is the one about object appearance. It takes as input a description of an object, for example, green rubber cylinder, and it feeds it and some noise here, and is trained using is trained as a conditional autoencoder, where the conditioning is essentially the language. And essentially, given this utterance, it spits out a 3D feature map of the corresponding object. Because at training time, you assume you have bounding boxes, so you know exactly, and you also have association between noun phrases and the corresponding object, okay, to be able to train those generative networks. And here is another instantiation, blue ball. And here's again the other corresponding 3D feature map that this network is going to give you. So you train it, as we said, supervised by mapping noun phrase to corresponding object 3D feature maps, cropped from the scene 3D feature maps. And here is the spatial generative network that takes essentially some random vector and a word, a spatial word, right, left behind, in front, and so on, and spits out an offset, a relative offset, dx to y dz, between the 2 objects that are concerned. And now we can put all those together, and I can generate, if you give me an expression, the green rabbit cylinder on the right of the blue ball, then I'll use my object generative network to spit out 3D feature maps, and then I'll use the special one to place them in a 3D canvas. And when projected, this 3D feature map better explain the 2D images. That's how it is essentially trained. And because we use stochastic networks, we can preserve multimodality in appearance, as well as multimodality in the spatial expressions. For example, here, I'm showing all different instantiations of what means for the red sphere to be front left of the blue cylinder. All these are different front lefts. And okay, here is some different viewing angles where you can see it. So each spatial expression has a canonical viewpoint from where it is computed, but because the network, you can see it's 3D feature map from any viewpoint, you can render it from any view point that you like. Here is again different instantiations of left behind, for the green sphere to be left behind of the blue sphere. Now, what can we do if we have those modular generative networks, at this time, you can give me an arbitrary long expression, like what you see here, and I'll generate the corresponding scene for you. For example, the red rubber cylinder to the left front of the blue rubber cube, to the left front of green rubber cylinder, the right front of the blue rubber cube, and so on. And we consider two types of renderings. Neural rendering, which is all the way from our network, and as you see, it's blurry, okay, because imaginations can be blurry. I mean, human imaginations are also not pixel accurate, but you can use the rendered features and do nearest neighbors from a dictionary of objects, and you see that you can retrieve the right ones. Okay. Okay, as you see here is the blue rubber cube and the blue rubber cube and the red rubber cylinder indeed, and the green rubber cylinder. While here, when it is, if you map the features all the way to pixels, things are blurry. The features of themselves can select the right object, all right? So they can do nearest neighbors correctly, and you can retrieve those objects and really put them in Blender and render them and then look at them. And you can do this for as long expressions as you like. And you can look at the generatives from all different viewpoints. And now you may say how this will help us in affordability reasoning. Well, it's going to help you because as you populate this 3D canvas, you can be checking whether objects intersect one another. And when they intersect one another, you can just go ahead and resample from your generative model till you find an affordable configuration, or till you decide that such an affordable configuration does not actually exist. So you can complain and say that, look, this doesn't make actually sense. So now, when we have a machine and tell it a red cube is behind the cyan sphere and in front of a red cylinder, and the cyan sphere is left behind of the red cylinder, then the machine can say this doesn't make sense. I actually cannot generate this configuration. And we compare our model with a 2D baseline, where it is again a generative network. It is compositional, but it's in a 2D space as opposed to 3D space. And you see we have a big difference. We train the baseline exactly the same way as ours. Why we have a big difference? Because in a 2D space, it's very hard to judge when a synthesis actually makes sense or is unaffordable by looking at bounding boxes, their IOUs, and so on. While in 3D is much, much easier. And in 3D also, you can generalize to dramatically different things that you've seen at training time, right? Right, because the laws of space actually generalize, that come for free when you reason in 3D space. Okay, so this is about affordability, VQA. Now, can we go ahead and try to use as little label data as we can while answering questions in the presence of images, not just imagination questions, but also questions about referential expressions, about object shapes and materials and colors and so on and so forth. So to be able to do that, we first need to discuss with you a way that just by looking around scenes, exactly what we talked earlier about this embodiment, how we train GRNs to go from a single image to a 3D feature map of the scene, we need to go further. We need to be able to organize the scene in terms of objects. And what I'm showing here is our next work that we looked at the scene from different viewpoints and used a 3D object detector that was jointly trained in the process, and was able to detect the objects and organize them into a library of 3D prototypes. And what is a 3D prototype? A prototype of an object, here essentially cluster 1, 2, 3, 4, 5. Every cluster is itself a 3D feature map, and you can render it from different viewpoints. And when you match an object to a prototype, you do rotation-aware check. So you try to find the rotation that has the minimum 3D feature distance to the prototype, so that a particular, for example, carrot can explain all different carrots in all possible rotations and scales and positions, as opposed to only a particular scale and orientation. So we call this a pose equivariant 3D quantization. And you discover this just by clustering in the 3D feature space automatically, okay? So automatically go around the scene, run objects, detect them, quantize them into prototypes, and minimize them, try to optimize for those 3D feature maps. These are essentially the embeddings of the prototypes that are not 1D or 2D, but rather are 3D. In fact, have 3 spatial dimensions and 1 feature dimension, and we minimize reprojection error. That's how this works. And so this quantization process now can be used to parse the scene into objects, cluster identities, and cluster orientations and scales. For example, this one here is cluster 17 with orientation 250, for example. And this representation is useful because this can emerge without a lot of labeled data. All right, and this can happen also in real, like more photorealistic scenes and so on. So that's one thing. Now, what is wrong with this type of quantization is that every differently colored paper will be a different prototype. Why? Because we haven't been able to disentangle color and shape. So this is what we'll do next. And such disentanglement is very, happens a lot in 2D images. Here is a famous paper, Munich Multimodal and Supervised Image-to-Image Translation, where a particular 2D image is mapped to a 2D content and 1D style code. Here in 3D, we're going to have a 3-dimensional content code and a 1-dimensional style code. So you can find the details in our ICLR 21 paper, Disentangling 3D Prototypical Networks for Future Learning. This disentanglement happens the same as 2D, but in a non-supervised way, using this content style autoencoder, where we take each 3D object feature map and map it to 2 separate encoders to spit out this 3D content and 1D style vectors, which will combine using adaptive issues normalization in the architecture and make the resulting feature map and then reconstruct and backpropagate the error. So now every object has been separated to the content code and style code. And what we're going to do with those content and style codes, we're going to do exactly what we did before. We're going to quantize them. And the styles are just going to be quantized normally, like 1D that they are. But context will use the same rotation-aware quantization that I described to you earlier. So here is how it works in practice. We'll have an image, and then the question will be, what is the color of the object to the right of the broccoli? And we'll train a semantic parser from a small amount of data. It works very well to spit out the program that we need to apply on our 3D representations. Our visual parser, which is essentially GRNN, 3D object detectors, and then shape and style disentanglers, will spit out for every image a set of object properties, where the object properties is the shape, this is the 3D content code, the style, the 3D location. And then we'll go ahead and apply this program into that 3D disentangled object representation. How do we do that? We'll say we want to match the style. Then I say, oh, the shape needs to be broccoli. So let me take the broccoli prototype from the vocabulary and try to match. And as you see, the matching is scale and rotation aware. So I'll be checking all scales and all rotations for my content, code. Then I want to find what is to the right. So for this case, I need to use only the 3D location of the objects. And last, I need to ask for what is the color. And then I'll check with my color code book and I'll realize that, yes, this is the red color. And exactly thanks to your disentanglement of the representations, you need very, very little amount of data. So what we show in this work is that you can answer questions. You can answer questions from novel content style combinations. You can also generate scenes exactly like before. And you can do this with very little amount of data. So here we show what can happen if you have only 10 or 25 or 50 training examples. And we show that the 3D model, our 3D model we just described, does better than the 2D neural symbolic model, despite adding disentanglement in the 2D neural symbolic model. And rotation aware and the disentanglement both help, both within domain as well as in one-shot generalization. So to summarize, this talk was about using 3D visual feature representations for a visual question answering with little data. Our time is also over. The benefit of those 3D representations that constraints about the 3D space comes for free. Of course, obvious next steps is that these representations should generalize to realistic environments, to much richer language domains. And beyond spatial constraints, we need to add physics and other sorts of dynamics during natural language interpretation. Thank you very much for your attention. And here are the 3 papers that I mentioned. And I want to thank also the students that worked actually to actually carry out this work that I just described today. Thank you very much.